There we go. So the lady says we're being recorded, so we're being recorded. All right. So we're going to pick up where you guys left off last quarter, and I want to talk about momentum and collisions, make sure we're all kind of on the same page. I know that I came in and subbed for you that one day, and to be honest, I have no idea where we ended up or what I talked about. So I'm just going to kind of start from scratch. So the first bit might be a little bit, yeah, we already know. But I want to make sure we're all kind of down with this because momentum is a big deal. It's super important, and we use it a lot when we're looking at how bodies interact, because it's all about how things, how the paths change of objects when they interact with each other. And that happens a lot, right? Anytime there's a force between two objects, there's going to be a change in momentum. So I want to make sure we're all kind of down with that. So I'm going to go ahead and switch my microphone to the other one so you can see the screen now. So hopefully when you're looking at this, you see the screen that shows the whiteboard. It says Physics 108 right now. So quiz for class. You can go ahead and either type this into the box, chat box, or if you want to unmute yourself and speak on it. What is momentum? And I'll take anything from something descriptive to an equation. What do you guys remember? All right, so I see Victor just hopped on and he said mass times velocity. What do you guys think? Sound right? Thumbs up?
Yes.
Yeah, that sounds right.
Yeah, we're sounding good? Okay, so the way that we define momentum is mass times velocity. We use the letter P for that. Hopefully you remember that. But for momentum, we got P. And it is just mass times velocity. So it is a vector. Momentum's a vector, just like velocity is a vector. So it was mass times velocity. So you can actually have a large momentum by either increasing the mass or increasing the velocity. And some ways to think about this, think about like a large mass but slow speed. Think about something like a huge oil tanker in the ocean, or like a train, you know, a huge engine with a bunch of cars behind it. That's going to have huge momentum, even if it's moving slowly. Because I guarantee you, you're not going to want to go step in front of a train that's only going 5 miles an hour, right? That's bad news. That train's just going to run you over. Even if it's only going 1 mile an hour and you stand put, you're still getting flattened, right? So it's got huge momentum, even though it's moving very slowly. But on the flip side, you can have something very small that's moving fast that has huge momentum. Like think about a bullet coming from a rifle, right? The round of a rifle, the actual lead in a rifle bullet, very, very lightweight. However, because it's traveling so quickly, such great velocity, when it impacts something, it can make serious, serious damage, right? It can like make huge holes in walls and things like that. So there's large momentum from small mass, but large velocity. All right, so momentum is mass times velocity. All right, how about this class, quiz for class? How about impulse? What do you remember about impulse?
That's like a sudden change in force or something like that, right? Or a sudden force.
Okay, so a change in force.
No,
There's for sure a change in force. So Ralph just said force over a certain time. Victor threw out derivative. There's a relationship, derivatives and integrals, calculus stuff. But yeah, impulse is really, it's a force over time. I think the way Ralph wrote it there, force over a certain time, is a really good way of thinking about it. So let me go ahead and write this up here. So impulse, we use J for that. It's also a vector. but it's actually the integral of f dt. And I just want to confirm that's about as low as I can write on the board, right? If I go lower than that, we're not going to be able to see it. Yeah, okay. All right, so it's actually force times distance. So the impulse, it's actually the impulse of a force, if you really want to think about it. And the impulse, that's the amount of force over the amount of time. So if you have a large force over a short period of time, it can still be a large impulse, right? This would be like if I took a sledgehammer and just whapped you in the knee real fast, like barely in contact with your knee for very long, it's still going to hurt. It's still going to do serious damage. The flip side of that is if you have a very small force, but for a long period of time, that can still create problems. So instead of taking a sledgehammer to your kneecap, this time what I'm going to do is I'm going to put your knee into a vise. I'm going to squish it between two plates. Okay. But I'm just going to start pushing really slowly on that. I'm not going to compress super hard. But if I continue to apply that force for a long time, kneecap is still broken, right? So this is another quantity that really has two things that matter to it. One is how great of a force, and the other is how long that force is actually being applied. All right, and when we talked about this in class, I know I mentioned this briefly. This was the whole, dropping a glass onto cement versus carpet, why it sometimes will break and sometimes won't. Think about that example of the glass coming onto concrete or something hard. All that force is happening for a small amount of time, right? As opposed to over a long amount of time when it hits something cushioned. And so impulse is really a good descriptor of how much damage can happen, how likely something's going to break from a force, and so on. So it's not just the force. You could actually have a force applied to you that would do no harm, but the same force over a longer period of time would be a problem. So we need to think about this when we talk about motion. It's not just force. Force matters, absolutely, the magnitude of the force, but also for how long that force is applied. Okay, so that's impulse, but then these guys are actually related. So let me run through the math again so you can see their relationship. All right, so I'm back to the board now. And what I'm going to do is I'm actually going to start with that definition of impulse. And I'm going to drop the vector arrows just because I'm tired of writing them. But we're going to remember that these things are vectors when they apply. All right, so we're just going to start with impulse is the integral of force. But we know from Newton's second law that force is equal to mass times acceleration. So let's just rewrite that real quick as mass times acceleration. I'm going to factor out that mass real fast because the mass should be constant. If we're talking about a force being applied to an object, like when we use Newton's second law, that was always a constant mass. So since it's a constant, I can pull it out mathematically. If it's not constant, we'd have to do things a little bit differently. But you guys are already used to this at this level in physics. We do all kinds of assumptions to make things easy, like no air resistance and all that. So we're going to go with the mass doesn't change. All right, so I know you now have taken a little bit of calculus, and you've done integral calculus. Most of you took it not with me, but with Larry last quarter. But what do you get when you integrate acceleration with respect to time?
Velocity.
Yeah, you get your velocity. But what I'm going to do here, I'm not going to write it as v. I'm going to actually write it as m times delta v. And here's why. When we actually calculate this impulse, there are bounds on that. It's a definite integral, right? We're looking at how long is this force being applied? Well, it's from time 1 to time 2, right? So I need to actually have some sort of a t initial, t final, which means if we actually do this integral, what we would have is v final minus v initial, hence the delta v. So this is why we actually talk about impulse when we're also talking about momentum and these connections, is because they are intimately related. I mean, look, we've got momentum is mass times velocity. Well, we saw that impulse is mass times the change in velocity. So you can kind of put that together. And what we've got is that impulse, J, is, I didn't want to write like that. That's what we just had, is actually equal to the change in momentum. So if there's a great change in momentum, then there's a huge amount of impulse, right? Or vice versa. So let me give you an example. Suppose that we're hitting a baseball. And I know you guys are going to get really tired of baseball examples, but I got no baseball. So this is the only place I can get my baseball stuff out. So think about we're hitting a baseball. And we've got a pitcher who's throwing it nice and heavy, 95 mile an hour. Okay, so we're going to go ahead and just sort of talk about this in our weird units. I don't want to try to convert to metric. So suppose that we've got this ball coming at us at 95 miles an hour, and they're not that heavy, right? They're, I would say maybe half a pound. I don't know, whatever. But let's just take that mass, call it easy, 1 pound, 100 miles an hour. Okay, so you multiply those together, and it's got a momentum of 100 mile pound hour, whatever weirdness. Okay, so now that baseball gets struck and starts flying the other way, but a little bit faster, right? Good batters will have it come off their bat faster than 100 miles an hour. So let's say it's coming off at 125. So let's think about what that change in momentum actually was. So let's put this on the board. We got the ball coming in. At the start, it's coming in towards the bat. And let's put some speeds on there, our values. So let's say we got our M is 1 and our V is 100. So in terms of its momentum is 100 of whatever those weird things are. Now on the way back, after it gets hit, right? So now here comes the ball off of the bat. Now, still got the same mass, but has different velocity. Let's bump it up to 130. So its momentum is going to be 130 of those whatever weird units. So what would the impulse be? Go ahead and type it in your chat window, or if you want to get on your speaker. What would the impulse be for this interaction? All right, so let's see. So Ralph's got minus 30, Cesar 30, Max minus 30. All right, so what do you guys think? Plus or minus 30?
It's final minus initial, right?
Okay, so we'd want to look at the final minus the initial, correct? All right, so Ralph just threw in a 230 with a question mark. Changed his answer. Okay, well, let me spare you this a little bit. It turns up, Ian, depends on where we set the origin. Turns out that's not true. No, origin doesn't actually matter, right? So here, think about it this way. What we have to remember is that this is a vector, okay? This is a vector. So think about how I have these arrows drawn. We can even use that kind of as our, here's how we're going to set this up. I think, Ian, let me just change my answer to you real quick. The only thing that will matter how we set our 0 is whether it's plus or minus, which direction we're going. But in terms of the magnitude, it won't affect it. So let's get rid of all this crap and make it an easier picture to see with just the vectors. So I've got a vector that's pointing, in my case, to the left. That's magnitude 100. Right? And then we end with one that's pointing to the right. That's a magnitude of 130. So we have to think about what would we have to add to this 100 to make it look like the 130. So we can even just do this graphically. I'm going to need 130, but I also need to counter that 100. And so you notice that that actually is 260. So there was actually an incredible amount of impulse here. We had to change the momentum, not just its magnitude, but its direction. And since these are vector quantities, that change in direction is also a big part of it. So that means that in the process of doing this, we had 260, let's see, it's mile pounds per hour. Oh my God. All I know is any of my physics professors back in the day would be cringing at that kind of a unit. All right, but we've got mile pounds per hour, 260 of them. Okay, so let's just think about this in terms of force then, right? If we think of this as impulse, this is a force times a chunk of time. Let's apply a constant force. So let's think about a reasonable amount of force that we could supply with a baseball bat.
So I have a question.
Yeah.
How come it's 260 and not 230?
Because I wanted to make it 260 for some unknown reason.
Okay.
No, that's me being me. I think probably in my head, I was thinking 130 for both of them. But yeah, so it's 230 pounds per hour. Okay, so that's kind of a weird unit. But basically, this is telling us how long we'd have to apply a certain force. So when somebody strikes a baseball well, you end up getting a lot of contact for a long time. The ball's actually in contact with it for a long time. And so what they'll end up doing is applying a decent amount of force, but for a longer period of time, which gets them that impulse. So I'm going to see if I can find online here real quick. I'm going to YouTube because I love me some good YouTube. I'm going to see if we can actually see like a slow motion contact between a baseball and a bat, because it's pretty impressive. And you can see actually how long they're in contact together because it's not instantaneous. It's probably not what you would expect it to be. All right, so while I'm doing that, since it's been a while since I've seen y'all, good stories. What's happened to you in the last little bit other than quarantine? Because I've heard enough of those.
For me, it's been nothing. I just been home all day.
Been home
It's
all
been
day
pretty
for
boring.
weeks.
Yeah.
I've been getting pretty good at that Call of Duty Warzone.
Nice.
All right, how many hours do you think you've logged on that in the last week, Bradley?
So I just downloaded it maybe 4 or 5 days ago, and it's probably been like, oh God, it's kind of frightening. But well over 24, that's for sure.
And that's all time you'll never get back.
Yeah, I've been reading too, so it's okay.
All right. Well, I found the video I want, but my computer's being really slow. I think it doesn't like the fact that I've been zooming all day. Oh, and Ralph, all right, Resident Evil 3 in 3 hours. That's impressive. And Ian, yeah, you and me both.
Yeah.
Lots of root beer.
Exactly.
Lots of root beer. No, I was actually in Hawaii when all this nonsense started happening. My son and I were over there for his spring break, and like Hawaii put in a quarantine for people visiting. And I was worried that it was going to be one of those, well, now we are going to have to like be stuck in a hotel room or something. I wasn't even sure I was going to be able to get back to Reno, but luckily I did. All right, well, this thing's being kind of a pain. So if I can pull it up, I think we'll take a break later. And if I can pull it up, I'll see if I can get it. But anyway, so impulse is really a change in momentum, which is also kind of cool that it's related, because now we can write Newton's second law in a different way, right? You already know Newton's second law as F equals ma. All right, but real quick, just check this out. We change that acceleration to a velocity. So it's mass times dv dt. All right, well, the mass is constant, so we can throw that in. So we got our force is equal to d dt of mv, which is momentum, right? So another way of thinking about Newton's second law, we can use F equals ma. It's totally reasonable. But we can also use F is equal to dp dt. And there are lots of situations where that's what we want to use, is the change in the momentum. So kind of interesting that knowing a force, you actually know everything you want to know about acceleration, but you also know everything about how the momentum is changed. So when two bodies interact, when there's a force that applies between two bodies, it's going to change their momentum in some way, right? So that's kind of cool. Now, I don't know if you remember this as well, but probably, I hope, is that we saw that momentum is conserved. What does that mean? When I say that, what am I talking about?
Energy, maybe? Like how energy is also conserved?
So energy is conserved. That's another place where we got conservation. So what does that mean if energy is conserved?
It just goes from something to something else. Like it can be created or destroyed.
Okay, yeah, that's a
good way of describing it, is that when we talk about energy conservation, is that we've got a certain amount of energy, it just changes form. And I know the analogy that I used in class with you guys was money, right? Like Victor just put what you start with and what you end with. That's that we've got a pile of cash. I can take that money and I can distribute to you in different ways, right? I can make sure everybody gets the same amount, or I take some from Ian and I give it to Jacob or whatever. But I can't just magically make money or have it disappear. Now, in the physics world, that's work, right? Work is we add it in or we steal it away, that kind of thing, right? So that's conservation. So conservation of momentum is the same idea. So if we've got a closed system, so we don't have anything outside that's affecting it. If we've got a closed system whatever happens in that system, the amount of momentum stays the same. So let's think about this system being the baseball and the baseball bat. Now, obviously, there was some stuff that got it going, right? Like the pitcher threw the baseball. But let's go with the baseball is out of the pitcher's hand, and we're going to look at baseball and then, I guess, batter and bat. Okay, so that's our system. And they've got a certain amount of momentum. Well, if the momentum of one of those objects changes, which we saw with the baseball, right? It started going the other direction. That means that there has to be a similar change in momentum to counter it out. All right, so like Ralph said here, if there's a collision or something like that, the momentum of the new object needs to be the same. It's not quite that the new object has to be the same, but the total has to be the same. Think again of that momentum as a big wad of cash in a pile. We might distribute it differently, right? The baseball cash, some of it gets shifted to the baseball bat, but there's always the same amount. So the question is, why? Why does it have to be conserved? I mean, it's great for us just to say momentum's conserved, but the question is why? Can we actually show it? And you can really easily using Newton's laws. So let's go to the board.
All right, so think about Newton's laws, and specifically, let's think about Newton's third law. So which one was the third law of Newton's?
The third law pairs,
One opposite.
Okay, what do you mean by the third law of pairs?
like what Ian said.
Third.
Okay, so Victor just typed in, for every action, there's a reaction.
Equal and opposite reaction.
Yeah, that's the one that, the way that most of us know the third law is for every action, there's an equal and opposite reaction, right? I want to be a little more technical. And so what I'm going to say is that if we have two objects that interact with each other, so let's have object A and object B. If object A applies a force to object B, then object B applies a force to object A that's exactly the same magnitude, just points in the opposite direction, right? So that's the whole, every action there's an equal and opposite reaction. So let's think about this and how we can turn this into a momentum kind of deal, because we now know how force and momentum are related. So let's just think about these guys. Let's call this object number 1, and this one object number 2. So what I know is that the two forces are equal but opposite. So let's use Newton's second law. And so I'm going to write here that M1A1 is equal to M2A2. So that's the magnitude of those two forces. But because they point in opposite directions, I actually want to make this a minus. All right, so this is Newton's second law, that F equals ma, combined with Newton's third law. All right, well, we can go through the derivation that we did before to get Newton's second law into the momentum form. But what this is going to look like then is that the change in the momentum of 1 has to equal the change in the momentum of 2, just with opposite sign. So that came from the derivation we just did. Well, if I move this to the other side, and kind of pull it out of the derivative here, I get ddt of P1 plus P2 has to equal 0. So knowing your calculus, what does this tell you? What does it tell you if a derivative equals 0?
That they're constants.
Okay, that it's a constant. So from this, what we just found out is that P1 plus P2 is constant. All right, well, remember what those things were. P1, that's the momentum of object 1. P2 is the momentum of object 2. And this just says that if nothing else is acting on them, right, we don't have anything outside that's affecting these things. It's just these two objects, so it's our closed system. If all they do is interact with each other, the sum of their momentums has to always be the same. Hence, they're conserved. All right, so that's why it has to be this way, why the momentum is conserved in a closed system. So this is going to be our friend, because this is going to allow us to figure things out without actually having to find accelerations and all that using Newton's second law. So let me give you an example.
So here's the scenario. Let's say that we're out on a really, really slick parking lot or a field somewhere that's really icy so that we can have, no friction. I know, no such thing. But we're going to go with as close to zero friction as possible. All right. So you're standing out on that field and I throw a football, right? So I'm going to throw the football and you catch it. So let's just think about what's going to happen. You catch that football, what's going to happen to the football?
It'll indent a little bit as upon catching.
Okay, so it'll deform a little bit. In terms of its motion, what's going to happen?
Come to a stop.
Okay, it's going to come to a stop. As long as you got good hands, right? You'll catch it, and I know you guys all have good hands. You'll catch it. Okay, so that football is going to come to a stop. Does its momentum change?
Yes.
Yeah, that should be the easiest yes answer in the world.
Yeah.
Right? Its mass doesn't change, but its velocity does, because it was coming at you at whatever speed I threw it. But then once you catch it, you drop its velocity to zero, so its momentum changed. All right, so conservation of momentum then says that you have to counteract that momentum, right? And this, Victor wrote this in the chat. I wasn't ignoring you, Victor. I just wanted to get there. He just said it's going to transfer the momentum to me. And that's exactly right. So now you have to go from zero momentum, because you're just standing there, to having the same momentum as what the football had on its way in. So let's calculate this. Let's see if we can figure out how fast you're going to be moving on that ice after you catch the ball.
All right. So here are some numbers. Let's actually do some specific numbers for this situation. So first of all, you're catching the ball, and let's say that you weigh 70 kilograms. Okay, so we've got a 70 kilogram person who's catching the ball. The ball itself, a football is pretty light. It weighs about 0.4 kilograms. Obviously, it depends what kind of football. And even a Tom Brady deflated football should still be about the same weight. That was for you, Bradley. All right.
So you got me with that one.
I'm sure that we share that in common, our displeasure with that football player. Although I think it's hilarious he's now going to be in Tampa Bay, but that's another story. All right, so here are the masses for you and the ball. Now, I'm going to throw this ball to you, and that ball is going to come in at 10 meters per second. Okay, so here comes that football, ready for you to catch it. All right, so let's do a little momentum before and after kind of argument. And so here's going to be our before the catch. So let's look at you and the ball. So in terms of you, your momentum, it's going to be your mass, so 70 kilograms, times your velocity, which right now is 0 meters per second because you're just standing there. So you've got a grand total of 0 kilogram meters per second. You're going to love doing these kind of calculations with an object that's stationary. Okay, so that's you. And then if we look at the ball, this one is going to be 0.4 kilograms times 10 meters per second, which gives us 4 kilograms meters per second. So grand total, we've got 4 kilograms meter per second. But remember, this is a vector, so we need to be concerned with which direction it's pointing. What direction is it pointing right now? All right, so Victor just said east. I like that, east or right. Either way we want to think about it. But yeah, so before the catch. So I'm going to write it up here just so that we can, because I'm starting to get a little bit low. So before catch, we've got a vector pointing to the right with magnitude 4. It's going to drop the units on it for right now. Okay, so that was before the catch. So now let's think about after the catch. So I'm going to leave a space here for after so we can see what's going on. But let's calculate that. So after the catch, okay, now the football, this is where we have to get a little bit careful, is that football and you are now together. So after the catch, we have one object. This object is you and the football in your hands. So if we think about this one, we know that its momentum is going to have to equal 4, because afterwards it has to look exactly the same. But we have a slightly different mass. Now we have 70.4 kilograms. It was your 70 kilograms plus the 0.4 kilograms for that football. So if we go and we calculate that velocity, at least its magnitude, right, the kilograms are going to cancel from the units, leaving us with just meters per second. So we have 4 divided by 70.4, which is actually quite slow. So notice that we were able to figure out how fast you're going to be sliding along the ice after you catch this football. All right, it's not much. And in reality, does this happen? Well, yes and no.
Because there's friction, right?
Yeah, there's always some friction, which is going to make it so that it doesn't quite transfer exactly like this. But I don't know if you've ever tried to like play sports on a really like wet field, really kind of wet and muddy. You'll have this happen where after you catch it, you'll still kind of move. A good example is actually with baseball. Like think about when you catch a baseball, your hand
will actually go back when you catch that ball, right? The ball comes in nice and hard and your hand goes back. You're able to stop it with your muscles, but there is that conservation of momentum. So you'll experience this even out in the real world when you're trying to catch something. Someone throwing a football at you at 10 meters per second, probably not, right? But there is the potential. And if the field is slick enough, you will go backwards.
So where does that momentum go after once you finally catch it and your hand like
it moves back. Where does that go afterwards?
Okay. So in that situation, like you were talking about, the ball comes to me and my hand goes back, but I stop it.
Yeah.
That's because now there's an external force that's being applied. What's applying that external force?
Your hand, right?
Maybe not my hand, but my body. Yeah,
Okay,
all the
I see.
muscles, everything in my body starts
Yeah.
applying an external force. And the important thing about the conservation of linear momentum was that it has to be a closed system. If the
Oh,
system
okay.
isn't closed, then momentum can change. And so for that momentary instant, there is that transfer of momentum, but then an external force gets applied by my body in whatever form, the muscles and all that. And that now brings that total momentum down to zero. It's stealing from the pile, right? We had that pile of momentum that we could use. My body then came in and snatched all that money.
I see. That makes sense.
Okay. So it's always this whole closed versus not closed is super important, because things like even like conservation of energy was only true in a closed system. If we started applying an external force like friction or something like that, it depleted the pile of energy money the same kind of way. So does that make sense, Max?
Yeah, thank you.
All right, cool. All right, so here's what I want to do. Let's change this problem slightly. All right, because you guys I know can catch, right? My brother, not so much. Total butterfingers. Total butterfingers. So I throw the same football to him. He's on the same icy field, so there's no friction. But he doesn't catch it. And in fact, he kind of does that whole, it's coming towards me, and sort of bats it backwards. So here's what happened with him. Instead of catching it, he actually made it so that that ball started going back towards me, but not at the same speed, right? He actually cut the speed in half, but it was coming back at me at 5 meters per second. So let's see about him. What's going to happen to his velocity now? But we're going to assume that he's the same mass, so we don't change that. But let's see what happens if you don't catch the ball. Even though when I say you, it's not you guys, because I know you will. It's my brother.
All right, so again, we're looking at before and after. So before is still the same, right? We still have the same 4 kilogram meters per second from the football that's being thrown. But let's look at after, because after now we have 2 vectors. We've got the football vector, and we've got my brother's catching vector, right? So here's our football, and there's the person. So they're now going to have separate momentums because they're no longer together, right? Butterfinger hands. He didn't catch it. He dropped it, which means there's 2 different things going on. All right, so let's look at the 2 separately. Again, if we look at the ball, we have the mass of 0.4. But now its velocity has dropped to 5 meters per second. So we do that multiplication. It's a nice, quick, and easy 2 kilogram meters per second. So let's put a 2 above the ball arrow there. So they're going that ball's got 2 kilogram meters per second. So how long does the other vector have to be? Go ahead and type it in or yell it out, either way. So Victor, you say half. Do you mean half of the 4, so also 2, or half of the 2? Okay, so half of the initial. So the balls is definitely half of the initial. And I don't know if you were thinking about trying to use the velocity from the last calculation. We can't quite cut that in half because this person isn't the same mass, right? Because we don't actually have the football in hand. But I can actually tell you a number for how much momentum that person needs at this point. Think about what has to happen. These two arrows have to add up to equal that initial arrow of 4. So how long does the person arrow, momentum arrow, have to be? Think of it like that other one. Okay, so Ralph just chimed in with 6 with the question mark. And that's exactly right. You should change that question mark to an exclamation point. It's 6. There you go. All right, so it's 6. Because if you think about it, I have to counteract these two. I need an arrow of 2 pointing to the right. And then 4 more to get me to that total of 4. So in this situation, in order for these to add up, because they're vectors, the momentum of my brother has to actually equal 6. Right? Think of, go with just regular plus minus like you're used to on the real number line. Plus 6 minus 2 equals plus 4. Okay, so now we can actually figure out how fast he's moving if we put this together. So, so for the person who dropped the ball, we know that that's 6. That's going to equal their 70 kilograms times their velocity. So you take 6 and divide it by 70. You get 0.08. So I don't know if you still have the number in front of you that we calculated when you caught the ball, but how does this compare? They're not quite the same. The other one was 0.06. So it turns out that by not catching the ball, you're going to end up moving faster than when you caught the ball. So if this is one of those situations where you want to get great velocity, you don't want to catch the object. The greater the velocity is going to come from repelling it. And this sort of thing happens regularly as well. If you have a bunch of repeated impacts that can get you moving faster than a bunch of repeated catchings, if you want to say. All right, so that's how we're going to deal with conservation of momentum. You basically want to look at before and after and make sure that you're in a closed system, because if you're in a closed system, then everything is good. So questions on that?
So it's almost as if the ball, because you didn't catch it, pushed you farther, faster.
Sort of. It's because of the rebound.
That's really what it is. It was the rebound that caused that, because some of the momentum is now going back towards. And so think about that. That was a negative, let's say. And to counteract that negative, we have to add some more. So that's really what happened. Had it been, I go to catch the ball and all that happens is I drop it, it wouldn't have been quite the same, because my mass afterwards is still going to be the 70 kilograms, not 70.4. But the ball itself would have 0, which means my total arrow would still be 4. So that's really what caused this, is by batting it backwards. That's what caused the big increase.
Okay, that makes sense.
Okay. Cool. Any other questions? All right. Here's what I want to do. Let's take a little bit of a break. I'm going to go ahead and pause the recording, and then we'll pick it up in. All right. So now that we've talked a little bit about the conservation of momentum, reminded ourselves how that worked, let's talk about collisions. Because this is usually where we worry about conservation of momentum. And collisions don't necessarily have to be physical collisions, like actual contact. They can be any two objects that get close enough that they then interact. So examples of non-contact collisions would be like satellite flybys. You know, when we send probes to Mars and all that, we'll sometimes send them by Venus so that they get a boost from the gravity, which we'll talk about when we get to gravity. But that's actually a collision. And you can calculate using the conservation of momentum, you can calculate new velocities and things like that. And in fact, that's how they decide on doing those flybys, is they reverse engineer it, and they figure out how they can get to, say, Mars or Jupiter, making use of these other bodies to give it kind of a boost. All right, so we're going to talk about collisions, and I want to give you just some terminology first so that we're all kind of on the same page. So in terms of collisions, we have a couple types. The first one is what we call elastic. All right, so like elastic band. Elastic. This kind of a collision is one where your mechanical energy is conserved. You don't actually lose any energy through this interaction. So these are theoretical. These are the ones that you can never have a truly elastic collision, but you can have almost, right? And the ones that are like the best are kind of like those ones I was talking about with satellites going by planets and all that. You can actually retain almost all of your mechanical energy in that case. All right, so that's elastic. There's also inelastic, and that's where you do lose kinetic energy. So let me go ahead and write these up on the board here real quick. So I'm going to write no loss of kinetic energy. All right, so elastic. Let me slide this just a bit. Elastic, again, we conserve mechanical energy. Inelastic, there's a little bit that's lost, or possibly a lot. When it comes to inelastic, we even have some subsets of that. We have what's called perfectly inelastic, and that's where the kinetic energy drops to zero. So this is a complete loss of kinetic energy. The objects stop. They stop moving. We also have completely inelastic. Which is different. Completely inelastic, this means that the objects stick together. So you can actually have a completely inelastic collision that's not perfectly inelastic. And a good example was the catching of the football, right? If you think about the football and the person as two separate objects, if I catch that football, we are now stuck together. We have become one new, bigger object. And that would be a completely inelastic collision. But it wasn't perfectly inelastic. Because remember, after catching it, we still moved slowly, right? 0.06 or 0.08, whatever meters per second. But we are still moving. Okay, so we've got elastic versus inelastic. And then within inelastic, you can have a couple different options. All right, so here's what I want to do. Let's look at that previous example, the catching of the football. But let's look at actually how much energy was lost in that completely inelastic collision. Okay, so let's go back. I'll pull up the numbers again, but let's look and see what happens in terms of the energy.
All right, so we should be back to the board now. And let's just kind of review where we were. Give you a second to catch this if you didn't get it. But let's review where we were with that catching of the ball. So at the start, we had no velocity. The person had no velocity, so had no kinetic energy. And the ball coming in did have some velocity, so did have some kinetic energy. So here we go. Let's go and take a look at that. So this is going to be an energy argument now instead of the momentum argument. So let's think about before the catch, and we're going to look at after the catch. So before the catch, let's look at the ball. The ball had kinetic energy that was equal to 1/2 its mass, which was 0.4 kilograms, times its velocity, which was 10 meters per second. So we have 1/2 times 0.4 times 10 squared, which was 20 joules. So that's how much kinetic energy that ball had. The ball did have gravitational potential energy. We're going to assume that there's no change there. Let's just go with it. The ball is caught at the same height as where it was thrown. Okay, so there's not going to be any mechanical energy other than just this kinetic. All right, so then what about the receiver? Well, if we kind of do the same thing, their kinetic energy, well, it was 0 because they were stationary. So the total was 20 joules at the start. And here's where an energy argument is a little bit nicer. You don't have to worry about direction, right? Energy is not a vector, it's just a scalar. So whatever the number is, that's the number. All right, so there's where we are before the catch. So let's go to after the catch. All right, so after the catch, now we had the ball and person together. Right, because we're going with, it was completely inelastic. We're actually stuck together again. So now we only have one kinetic energy we have to calculate. Well, but it's going to be the 1/2 times its mass, but the mass of the ball person combo is 70.4 kilograms. And the speed we had dropped down to 0.06. All right, so you put that into your magical TI-89 or favorite computation device, and we get 0.13 joules. All right, so take a look at that. Look at how much of that energy was lost. We went from 20 down to 0.13. That's less than 1% remaining. So almost all of the energy went away. So I guess the question is, where did that energy go? So what do you think? Where did that energy go? Where did that 19.87 joules go?
like Victor just said, sound and thermal energy. Sometimes it gets hot in your hands when you catch a ball.
Okay, so for sure there's going to be some sound. You're going to hear that impact of the ball into the hands. There will be some thermal energy for sure.
I was going to say heat. I didn't know that sound was another. I mean, I thought that was interesting.
Yeah, and we'll talk more about sound when we get to that chapter later this quarter. But sound is energy that's coming out as a pressure wave, basically. Well, another thing, and this is something that you mentioned before, Bradley, is the deformation of the football. That football is going to be depressed, like as you grab it.
As you grab that football, you'll squeeze it a bit. Some of the energy goes there. Some of the energy goes into compressing on your hands, right, and things like that. So a large amount of that energy goes away because you caught it. All right, so there's an example of how much energy can actually get lost in a completely inelastic collision. It's not perfectly inelastic, right? It didn't drop to zero. It got close, but it didn't actually get all the way to zero. Okay, so let's think about the second aspect. Remember that other one where my brother didn't catch the ball, but actually kind of knocked it backwards? Now, that one obviously is not completely inelastic. It's not going to be elastic either, because that's a theoretical. My question is, how close was it to being an elastic collision? So let's run the numbers on that.
So that scenario, if we kind of go back to the before and after, the before is going to be exactly the same. This is identical, right? We've got the same ball coming in at the same speed. So it's got 20 joules. My brother's got no kinetic energy. So there's a total of 20 joules. But now in the after, this is where we do have to look at them individually, because now the ball is moving separately from my brother. So let's look at these two. So for the ball this time, its kinetic energy is going to be 1/2 times 0.4 times 5 squared, right? Because it was knocked back at 5 meters per second. All right, well, you run the numbers on that and you get 5. So of that original 20 joules of mechanical energy, the ball still has 5 of it. So already you can see that we're losing less energy than we did before. Because the other one, once we were all said and done, we had a total of like 0.13 joules. We're already way more than that, and that's just this ball. So now let's go to the person who dropped it. So Butterfingers here, their kinetic energy, well, their mass is still the 70 kilograms. And their velocity, if I recall correctly, was 0.08 meters per second, what we calculated. So you run the numbers on that, and you get 0.224. So the total now, if we actually look at this, the total afterwards, we've dropped to 5.224 joules. So still fairly inelastic, right? I mean, we lost a lot. You lost about 3/4 of the energy, but way less than what we lost before, right? Anyway, so there's that guy. Now, here's going to be the challenge question. This one's going to be a little bit tougher for us to do. But here's what I want to know. If it had been an elastic collision, right? Best case scenario. Elastic, where all of the energy is also conserved. I want to know how fast, what velocity is that rebounding ball going to have?
So what I mean by that, let me just show you what I'm talking about. So the ball's coming into me. I don't catch it. I let it just hit my hands and bounce off. But what I want is for this to be a completely elastic collision. So that theoretical vest. So whatever kinetic energy that ball has coming off my hands and whatever kinetic energy I end up having still has to add up to that 20 joules. Okay, so let's see if we can figure that out. Let's see if we can figure out how fast that ball has to actually be coming off my hands if it's a completely elastic collision. Right, so since this is a theoretical best, that's why this has to be me, because none of the rest of you could do that. Right? I'm the only one who's like theoretically awesome. Yeah. Okay, so let's just see how this plays out. So let's go back to the board.
So we already know our target is 20 joules. So let's see what that's going to have to look like in our after. All right. So if we just look at the energy argument here, what we know is that we started out with 20 joules, and we need that to be the same for the afterwards. So we're going to have to put two velocities in here. So let's put the football. We got 1/2 times 0.4 times, I'm going to put V sub F. So that's the velocity of the football. And then we're going to have 1/2 times 70 squared times V sub P squared. So we've got velocity of the football, velocity of the person. Those are our two velocities. But there's the energy argument. I want the exact same amount of energy afterwards as what we started with. All right, but you may notice that there's a bit of an issue here. Think mathematically, what's the problem?
There's two variables.
Yeah, we have two unknowns. We got ourselves the velocity of the two individual people, which means we need some other equation that relates them. Well, what do you think we're going to use?
Momentum.
And yeah, let's use momentum. We know momentum has to be conserved because it's a closed system. So let's do a momentum equation. So for the momentum, we know the initial amount of momentum, right? We had already calculated it was the 4 kilogram meter per second squared. That was all the momentum in the football. And when we split it up, this has to be the sum of the momentums of me after I've knocked this ball away in this perfectly elastic collision, and the momentum of the football itself. Okay, so if we go to me, so here's my mass, 70, and I'm going to multiply that by my velocity, 70 times VP. And then for the football, we're going to have the same thing. We're going to have the 0.4 times V sub F. But you'll notice I didn't put any kind of a symbol in there because it's not a plus. I know you might be thinking, right, but we're combining them. We need to add them. It's actually a subtraction. Uh-oh. Why?
Final minus initial.
It's not a final minus initial because the way to think about it here is the final is just the right side of the equation and the initial is the left.
Is
But
it
I like how you're
because
thinking.
the ball is coming towards the person?
it's all about direction. Max, you're kind of on the right track. You think about the momentum. Remember that this 4 kilogram meters per second squared, momentum's a vector. So we do have to pay attention to direction. This is the football coming towards me. Afterwards, I'm going to continue moving in that same direction, right? When I get knocked by this football, I'm going to move in the same direction. I'm moving to the right. That's why these have the same sign. The football, after the collision, is coming the other way. So that's why it gets the minus. That minus is purely from the fact that these are vectors. So this illustrates what I was talking about before about how the energy argument's a little bit easier because you don't have to worry about directions. Momentum, since it's a vector, you have to be very careful with this. And I'm just going to tell you that the majority of the mistakes that you make with momentum are going to be from that, where you have a plus instead of a minus or vice versa. So just be really careful, be mindful of that, and watch out for it. All right, well, this now gets our system. If I kind of just do a little simplification on these guys, the top one, we get 20 is equal to, let's see, I've got it written down here, 0.2 VF squared plus 35 VP squared. The other one, we've got 4 is equal to 70 VP minus 0.4 VF. And there's our system. So take one of them, solve it for one of the variables. Take the bottom one, solve for one of the variables. Fire it into the other. And once you solve this system, what you end up with is that the velocity of the person is 0.11 meters per second. The magnitude of the velocity, right? And then the velocity of the football is 9.89 meters per second. So it's coming back just about as fast as how it was thrown in this elastic collision. And notice that I am going backwards, but I'm going backwards a little bit faster as well than before. But that should kind of make sense because we're not losing any energy. We still have all the energy we started with since this is an elastic collision. So that's why I'd be moving a little bit faster in this best case perfect scenario. I do want to point out, you'll notice that those two add up to 10, which was the initial velocity. That is purely coincidence. Purely coincidence. Just how it kind of worked out. It's actually a rounding issue more than anything else. So that's not going to be the case in general. But you can also see some of this if we actually have objects that are similar mass, you can see this a little bit better. So I have something I want to show you.
So we're going to come back to this other picture of me. Let me just kind of move this. All right. So have you ever seen one of these before?
Mm-hmm.
Yes.
Yeah. So these are called Newton's cradle. Obviously, it's a cradle because it kind of looks like, you know, a baby that can rock back and forth, right? And then, of course, it's Newton's cradle. It's named for Sir Isaac Newton. But anyway, so these balls are all roughly the same mass. They're all roughly the same size and all that. And you've probably seen how these work. I'm going to pull one of the masses back, let her go. And you see they kind of do this dance where they go back and forth. All right. Well, this is a really good example of conservation of momentum. And I want you to kind of just sort of follow this through and think about how this works. So this one that I pull back, what I'm doing in the context of physics, if we want to throw the words on there.
Potential energy.
Yeah, yep, exactly. I just threw some potential energy into this. What kind of potential energy?
Gravitational?
Good. It's gravitational potential energy. I've increased its height. You may not be able to see it so well, but it has gone up a little bit. So I've increased its mechanical energy by making potential energy, which means, of course, when I let go, it's going to convert that into kinetic energy, and we'll see, some velocity going, right? As it falls, it's going to gain more velocity because it's giving up more potential energy. So when it comes back down at this point, it's going to have as much velocity as we're going to get from the potential energy here. You could take your good old MGH, set it equal to 1/2 mv squared to actually figure it out, right? But it's going to have whatever its velocity is, which means it's got momentum. Now, when it comes and it hits this, this is our closed system. This group of 5 objects are the closed system. So let's just kind of follow what happens. This is going to have a certain amount of momentum. Let's call it A. No, P. It's got a momentum of P. That comes down and it hits. It's going to transfer its momentum to the second ball. So if the rest of these weren't here, what it's going to want to do is just go up like the other one was coming down. I'll even show you. All right, so I'll remove those others. And you see it just bounces back and forth. So one's transferring its momentum to the other. And since they're the same mass, basically we're just swapping velocity from one to velocity of the other. Now, it's also not completely elastic. You hear it, right? You actually hear the clanking. That's telling you that there's some energy loss and all that. And you see that it's slowing down. We're losing energy, also friction through the strings, air resistance, all that. Okay. Well, now when I put in another ball, so think about what happens. This first one came down, hits the second. The second one wants to go this way and wants to go up, but it can't. It's getting blocked by this guy. So it transfers its momentum into this third one. And what we'll see now is that the middle one doesn't move. And the outer ones are moving just as if that middle one wasn't there. Well, maybe not just as if, but kind of close, right? All right, well, you throw in a fourth one. Now that third one can't move. It runs into the fourth guy. I'll show you real quick for a little bit, but ooh, watch, yay. And then when we get to our fifth one, same thing. So basically, it's a chain reaction of momentum shifts. Momentum from the first one goes to the second, which then gets passed to the third, then the fourth, then the fifth. Since there's nothing else blocking this fifth one, it moves up. All right, so now check this out. What if I pull 2 back? What's going to change now in terms of energy, momentum, all that good stuff? What do you guys think?
2 are gonna bounce.
That's what I was gonna say.
Okay, so we got a couple of things. The 2 are going to bounce out. So let's just kind of do the, let's see, Ralph just says only one's going to bounce. So let's just think about this in terms of energy. In terms of potential energy, I now have twice as much potential energy in this set of 2, if they're the same mass.
And then to equal it,
And when it comes down here, that doubled of the potential energy is going to be an increase in the kinetic energy at the bottom, right? Which means an increase in velocity, which means an increase in momentum. And so that same increased momentum needs to be transferred over here. So we have a couple options. If it's just one ball that leaves, what's going to happen to that one ball?
the potential energy at the end will be much higher. So it's
Okay.
going to raise
Exactly.
in height.
Because that momentum transfer, way much more momentum into this smaller mass, means increased velocity. Increased velocity means more kinetic energy, which means as it gets changed into potential, it would go higher. So if it's just one, as that one comes off, it's going to have to go up higher than the other 2. All right, what if it's 2 balls? What's going to happen to these 2 balls if it's 2 that move? What do you think in terms of the final height?
I mean, almost the same, right? But there's a little degradation in the or loss of energy in the system, so it'll slowly get smaller and smaller.
Okay, so we'll definitely experience a little bit of loss because we have to. In the perfect world, it would be the same height, right? So if these two were launched at this height, the other two as they leave would be same height. What if it happened to be three that move? What if all three of these guys tried to move? Well,
Then the
now,
other two would go higher, maybe.
okay, so now we've got more mass
So it'd have less
for that
height.
same momentum. So we're going to have less V. Smaller V means less kinetic energy, which means less potential energy when we trade. So it definitely depends how many balls end up getting transferred. Well, here you go. I'll just show you. So here come two out. And you can see that
That's pretty cool.
two leave. And they are going to basically the same height. Let me do it again now that you know what to expect. Right? So here's this height. And you see it's about the same height, which is what we expect, but with that little bit of loss like Ian was saying. All right, so one transferred to one, two transferred to two. What about three? What do you think is going to happen if I pull three of them back and let them go?
I think it's just not going to be stable anymore. It's just going to go crazy.
All hell breaks loose and things fall apart.
Yeah, like kind of like right now with coronavirus.
Yeah, right. It's so we're going to do the coronavirus of collisions here in a second.
Yeah.
Well, okay. If we kind of follow that same logic, if I pull three back, we should expect to see three go the other way.
But we don't have a middle one.
Right, but we don't have three. So that might be kind of where Max was going with the all hell breaks loose. Well, I'll tell you what. Let's see. I'm all about experimenting. So I'll pull three back. Here we go.
Still two.
Whoa.
No, three, yeah. So the middle one stays.
Okay, so I'm going to mute you guys for a second just so that it will stay on the video. So do me a favor and don't say anything for just a minute. I'll unmute you in a second. Okay, so we're going to watch this, but watch the middle one. Keep your eye on this middle guy right here. And in fact, I'm going to try to keep my finger where that middle one was. Okay, so you can kind of see my finger there is where the middle was. And watch what happens. Oh, hits my finger, of course. Let's try that again. All right, here we go. Okay, so feel free to unmute yourself if you want to make a comment. But what did you notice about that middle ball? Where did it actually go?
I
Both
think
sides.
it still moves, huh?
Yeah, it keeps moving back and forth. So, kind of an interesting thing, right? So why is that happening? Well, it's that same idea of ball one is transferring to ball two is transferring to ball three and so on. So kind of think about it this way. When I dropped it, well, when we dropped one, it went from ball A to B to C to D to E, right? So it was a 1-to-1, 1-to-1, 1-to-1. When I dropped two, think about what B did. B gave its energy to C, which gave it to D, which gave it to E, right? So this end one corresponded to this guy. When it got down here, A gave it to B, which then gave it to C, which then gave it to D. So that's why those two flew out. And the same thing's going to happen to these three. All right, so the middle one, C, gives its energy to E. B gives its energy to D. And then A gives its energy to C. All right, so what if I try, I'm going to try this. It doesn't usually work. I'm going to try 4 of them. What do you expect to see?
Them almost looking like they stick together.
Okay, so it should look like they stick together. In fact, we should expect 4 to come out, which would be these 4. When it comes back, we see another 4 go out, which is these 4. So what it should really look like is that these middle 3 are always together. And it's these outer ones, they get left behind. So let's see if we can do this. Did you see it?
Mm-hmm.
That's pretty
Yeah.
cool.
Isn't that kind of wild? So
Yeah.
this is a great, simple little demonstration of collisions and how that energy gets transferred as we go from one to the next. Anyway, all right, so I'm going to put my screen back up here so y'all see me. Although that was really good advertisement for the Seattle Mariners. Go M's. All right, so the next thing I want to show you, though, is what about collisions that are not one-dimensional, right? Because all this stuff has been one-dimensional. Even you think about that Newton's cradle, it was all just motion going this way. And we can have collisions that are in 2 dimensions or 3 dimensions. And so the question is, how do we approach those things in that case? But I think you probably know. What do you think we're going to do if we go to extra dimensions? Oh, actually, before you answer that question, I want to go back. I just noticed on the chat here, Victor said, it looks like it's losing energy faster with the 4 moving than the 3. And you're absolutely right. We definitely did see that the energy was going away faster. Why do you guys think that was? Why do you think that pattern kind of died out and degraded faster when we had 4 as opposed to 3 versus 2 versus 1? Any ideas?
Takes more energy to move more masses than just one.
Yeah, it's definitely that energy. I don't know that it's necessarily it takes more energy, but it's in each one of the collisions, in each one of the transfers, there's a loss of energy. And when we had the 4, remember how I was talking about, the first one transfers it to the second, to the third, to the fourth, and like there's that huge chain. By the time the first impact ball trades its energy out, there have been more subsequent collisions. And so you end up losing more energy in each one of those transfers. If this was a perfectly elastic setup, if we could be in that perfect world, we wouldn't have noticed a difference. We would have seen it just keep going forever, but this is the real world. And every one of those did cause a loss of energy. So you definitely saw that, right, Victor? That's what was going on. And it really is. It's just energy. That stockpile of money was being stolen. Every time there was a collision, that was a hand coming into that pile of energy money and taking some out, which meant there was less to be used to keep the pattern going. Anyway, good observation. I'm glad you mentioned that. All right, so let's get back to this question I had. Like, what if we've got these 2 objects and instead of them coming in like that, right, for a collision, what if they come in like this or that, right? Or something like that where they're not actually in line. So how do you think we're going to approach that? Thoughts?
Dot product.
Dot product. Oh, you're overthinking it, Bradley. But I like where you're going. You're definitely a mathy guy. But you're on the right track. Because where do dot products come up?
Vectors.
With vectors. And that's exactly what we're going to have to do. We're going to have to remember that momentum is a vector, right? I mean, that was already important even with the just one-dimensional. But now if we have 2 things coming together that are not in a line, we really just have to break it into components. and do a component by component calculation, just like you've done for anything. Like go back to last quarter when you were dealing with the class with Kathy, you saw that there were times when you had to break it into an X component and a Y component, like when you're talking about something on a ramp, right? And you would always break it into, well, what about a normal piece versus an orthogonal piece parallel to the path, right? We have to do the same thing here. So let me give you an example. Let's say we've got two cars that get into an accident at just an intersection. So it's one of those where driver A wasn't paying attention, didn't see the stop sign, and just drove through. All right, let's look at how we would approach that. So I'm going to go back to the board. Okay, so now let's look at this scenario. So let's say we've got a car that's coming down this intersection. Let's say that it's 2,000 kilograms. So a metric ton. And let's say that it's moving at 50 miles per hour. All right, so we got that truck cruising down 50 miles an hour. Now, there's a second car, and this second car, say, is coming from over here. And totally doesn't see the stop sign, right? And this car, let's say it weighs 1,400 kilograms. And it's moving at 35 miles per hour. All right, so we got those two coming, and they end up colliding. And in the process of this collision, the two vehicles get fused together. So basically, they get stuck together. They become one particle. So this is going to be an inelastic collision, and it's going to be perfectly inelastic because they are going to stick. All right, so just by looking at it, can you give me a general idea of which direction it's going to go? And let's go with north is up, west is to the left, kind of like usual. Once these two come together, what general direction are they going to be heading, do you think?
Southeast.
Southwest.
Or, yeah, west.
Yeah, southwest.
So southwest, so kind of like how I've got my pen, somewhere in there, right? It's going to be doing something like this. As they come together, they're going to go bam. So we should expect that there should be a resulting vector, momentum vector that looks something like that. All right, so definitely towards the southwest. So let's see if we can figure this out. All right, so here's what we're going to do. First of all, this was horrible. I gave you miles per hour. Again, I know, but I gave you miles per hour, which means we're going to have to do some conversion because we really want to make sure that we've got this in the right units. So what we really need is for that to be in what? Instead of miles per hour, what units do we need this velocity if we're going to make any reasonable calculation?
Meters per second.
It's going to have to be meters per second. Okay, so meters per second. Ugh. Well, here's your conversion. I'm going to do the conversion down here and then erase it kind of not real quickly, but kind of quickly because I want to keep this picture. But let me just show you how we're going to do this conversion. So like the 50 miles per hour. All right, so again, to get to your seconds, we need to convert the hours to seconds. And 1 hour is 3,600 seconds. And then we need to go from miles to meters. I don't know, does anybody know roughly the conversion of miles to kilometers?
Here, miles to, 1.609344 kilometers.
Okay, so I'm guessing that was with a little help from Google or something.
Oh yeah, that's Google.
Yeah. So, which is all good. A really easy one to remember is it's about 5 to 8. 5 miles and 8 kilometers is about the same. That would give us a 1.6 in that number that Ian just rattled off. And you may remember he said something like 1.609, blah, blah, blah. So 5 to 8 is pretty good. So what I'm going to do here is I'm just going to say, so 5 miles is about 8,000 meters. Right. So 5 miles is 8 kilometers. So that's about 8,000 meters. So this will get our conversion to meters per second. All right. Well, my trusty black box here tells me that that is around 22.2. All right, so that's the velocity of that car that's coming south towards the intersection. All right, well, the other one is easy enough. Similarly, all we have to do is, in this whole conversion, instead of 50, make that a 35. So if you change that to a 35 and do your calculation again, because all the conversions are still the same, you end up getting 15.6. So I'm going to put that in here, 15.6 meters per second, where the other one was 22.2. All right. So again, I apologize for giving you miles per hour. However, in the real world, if let's say we're working for CHP or something and we're doing some sort of a accident investigation, we're going to be concerned about miles per hour. That's what we want, not meters per second. So, but regardless, we do a quick conversion, we're good. All right, so let me go ahead and erase this conversion. Hopefully everybody got it. If not, go check out the video later and you can see it. So what I want to do now is think about these momentums as vectors. So let's say that this is car number 1, the one up top. Its momentum, so P1, its velocity vector is straight down. So it's not going to have any momentum in the x direction. And in the y direction, it's going to have negative. It's all going to be negative, but it's going to be negative 2,000 times 22.2. So I'm just breaking it into components. I mean, you've done this a million times, right? Think about how often you've done this with things before. It's exactly the same idea. So if I go ahead and do that multiplication, I get 0, negative 44,400. So that's kind of big, but I mean, it is what it is. I mean, we've got a large mass. 2,000 kilograms is not a small thing, and it's moving at a pretty good clip. So, but anyway, so there's for vehicle number 1. For vehicle number 2, we're going to do something similar, but this time all of its momentum is in the negative x direction. So we're going to get negative 1,400 times 15.6. And then in the y component, it's 0. So same kind of story. Do that multiplication, and what we end up with that vector is a negative 21,840. And then 0 for its second component. All right, so there are 2 independent vectors, which means the total momentum at the start. So I'm going to write that up here. So P initial, it's the sum of those two vectors, which is negative 21,840, comma, negative 44,400. So I literally just added those two vectors together, component by component, and that gives me my initial momentum at the start. All right, so any questions on that before we move to the where are they moving afterwards, what kind of velocity and all that? Okay, I will take silence as go for it. All right, so there's our initial momentum. Now, if we assume that there's no loss of, if there are no external forces, so no friction or anything else, and this is a closed system, then this is also our P final. So whatever we calculated initially for our momentum is going to be the same as what we have at the end. So that's kind of handy. All right, so now the question is, what direction is this going? How fast are these things moving, and so on? So let's remember what this is. This is mass times the new velocity vector. So we've got minus 21,840, comma, minus 44,400. That's going to be mass times velocity. And since these two things have fused together, we know their total mass is 3,400 kilograms. So if I just divide by 3,400 kilograms, so it's going to be 1 over 3,400 times P, that will actually get me the velocity vector. So let's take those numbers and divide by 3,400. And I apologize for not having these numbers handy right away. I am using my calculator as we go. That's because when I ran these numbers earlier, I had different values. I didn't want to make you guys erase something halfway through. So anyway, so we're going to get minus 6.42 for the first component. And then the second component, we get 13.06. So minus 13.06. All right, so there's the velocity vector. That's the velocity vector for the post-crash amalgamation, right? Those two cars that are now stuck together are moving in that direction with that velocity vector.
Can we also apply the Pythagorean theorem to the momentum and then solve it?
When you say apply the Pythagorean theorem, what do you mean by that? Can you explain that a little bit better for me?
Just for the momentum, add them, or like do they just use the Pythagorean theorem and find the basically the what's it called, the resultant?
Oh, I got you. So like if we were right here at this stage,
yeah,
and then we do the Pythagorean theorem on there, that'll give us the magnitude of the momentum.
Okay.
Which then, if we divide by the mass, will give us the magnitude of the velocity. Yeah.
So that would be okay. I see.
Because that's what I'm going to do now. Now that I have this momentum vector or velocity vector, I'm going to find its magnitude, which is basically Pythagorean theorem. So Max, what you're talking about is doing the same thing, but just in a different order.
Yeah.
But yes, that would definitely work as well.
Okay.
So let's see what that speed is. We've got that velocity vector. So if we use the Pythagorean theorem or the distance formula or whatever you want to call it on this guy, we can get the magnitude of this velocity. So we find out that its speed is actually 14.55. So it's slower. I mean, if you go back and you look at the two numbers, the total resulting velocity is smaller than the two individual velocities, but that shouldn't surprise you because we've got this thing now stuck together, so it's a much larger object. And even conservation of momentum there suggests that there should be a velocity drop. Plus, those two velocities are not going in the same direction, so they're not really building upon each other. And then if we want to figure out what direction it's going, do you remember how you can find directions from components?
Tangent
Tan inverse of
Yep.
y over x.
Good. Yeah, you do the inverse tangent of the y over x. So if we do tangent inverse of this guy, now you do have to be a little bit careful about this. Hopefully you remember that when you do inverse tangent, the angle that you get is going to be in either quadrant 1 or quadrant 4. And in this case, it's going to be a quadrant 1 angle, which isn't the direction that we're going. It's opposite of the direction we're going, because like if you calculate this, you get 63.8 degrees.
Add 180.
But that 63.8 is actually off of the vertical. So if we were to come back here and draw that arrow, it's this angle that's 63.8. So it's actually going more. Nope, I lied. That's not that angle. That's this angle. Apologize for that. I didn't think about my geometry on that. So it's going more south than it is going west. But that should totally make sense, because if you think about it, the truck or car that was going south had way more momentum than the one that was heading west. And so it's going to kind of drive what happens. All right, so we just calculated, we figured out where it was going and what its velocity is. So that's how you can deal with these things if you're in more than one direction. You can just kind of put them together.
I'm switching
So-
cameras because I'm going to give you some truth here that you need to see my face for. All right, so remember at the very beginning, I gave it to you in miles per hour. We went through that whole conversion to meters per second. Okay. Had we left it as miles per hour, we would have gotten the exact same angle, same direction. Nothing would have changed there. And the magnitude of the velocity would have been the equivalent to what we just calculated, but in miles per hour. So even though technically we want to make sure that we're in good old meters and all the metric stuff, we don't have to be, as long as we're consistent. If you want to use speeds in miles per hour, use them in all the way through, your end result will still be in miles per hour. Same thing with mass. If you don't want to do kilograms, like if I had given this to you as cars that are certain pounds, don't change them to kilograms. It doesn't matter. And the reason that that works is, think about momentum. It's mass times velocity. That's a linear relationship. So if you double m, the end result is doubled. So think about like those conversion factors, like the 5 to 8 kilometer to mile thing. Okay, if I multiply by 8/5, my end result is multiplied by 8/5, which means I'm at the same place where I started. All right, so it's useful tips from Bruce. There's no reason to go all the way to a different unit in this situation because of the fact that it's a linear relationship. If we were doing the energy argument, we do have to worry about that, right? Because we've got 1/2 mv squared. Then you do have to be a little bit careful and make sure everything's fine. In terms of the masses, you're good, because that one's just a linear relationship with m, but with the velocities, it's not. So take that as what it is. It's a great tool. It's a great shortcut, but you have to make sure that you know you can be using it. because it doesn't always work. And I've got a lot of those. I think I've shared a lot with you guys over the course of calculus and pre-calc, those little tips that don't always work, but in this situation do. This is one of those. Okay. So if you want, remember when I did that first momentum and I had whatever, was it pounds, miles per hour nonsense? That was fine. I knew it was going to be okay in the end. And that's why I didn't bother changing anything. So anyway, use it or don't, but be very careful with that. All right. So how are we feeling about collisions? Not too bad.
Pretty good.
Hopefully this is kind of reminding you of some of the things you talked about at the end of the quarter, last quarter, which probably feels like half a year ago, right? Now that we're all in this quarantine thing, weeks feel like months. So, but anyway, hopefully that kind of brings that up. So I'm going to stop at this point since we didn't really take much of a break and I'm getting kind of tired, I'm not going to lie. We're going to go ahead and stop here for today. But on Wednesday, we're going to kind of pick up where we are right now, which is talking about when we get these multiple particles that are coming together. Something we want to talk about is what's called center of mass. You're going to like center of mass because it's going to allow us to do simple calculations even when we have a whole bunch of stuff. So we'll talk about center of mass and how that all works, which will finish us up for chapter 9. So we're doing exactly what I had hoped, which was kind of get through 9 today as your review before we start moving into the next sections. So yeah, so with that, have a great rest of your day. I will be, like I said, putting all kinds of stuff up on onto Canvas tomorrow. But other than that, I'll see you guys Wednesday around 3. All right.
Right. Thank you.
Have a good one, guys.
You too.
Have a good night.